Hi, everyone, and welcome back to our summer series of Dome to Home, bringing the wonders of the universe right to your desktop.
Hi,
Before we
everybody.
start, Fiske Planetarium would like to take a moment to assert that we stand with all of those who are fighting against injustice of any kind. This is a time for action, active listening, support, and reflection. Long dismissed voices deserve to be heard, now and into a more equitable future. So today, Nick and I will be spending time talking about the science behind rainbows, which could not be more fitting than right now, during Pride Month. Let's
Absolutely.
get started.
What we can see here is that we're looking at actually a beautiful view of a parking lot on the CU Boulder campus. We've got the beautiful double rainbow. Perfect view to begin our show today on rainbows.
So let's start with the most basic question. What is a rainbow? Well, a rainbow contains all of the colors that we can see with our eyes. So why does a rainbow always occur after a rainstorm? To understand this, we first have to understand some very simple properties about light. First of all, a color is defined by its wavelength of light. So Nick is putting up a picture on the screen, and we can see that blue light has a much shorter wavelength than red light. And this brings us to some interesting consequences. When this light goes through water, it gets refracted or bent. And we have another picture to show that. So you see the sunlight coming in from one end, and it goes through the water and it gets bent and exits out a different angle. And so each wavelength, each color, gets bent at a unique angle. See, blue light here is bent at 40 degrees, while red light was bent at 42 degrees. This makes it so that when all of the light enters water at once, it will exit in a split formation, much like this Pink Floyd album. Let's cover up the rainbow and imagine that this white light would continue. It would just keep going on its trajectory if not for this prism, where it bends the light downwards. And now you can see each of the individual colors that make up the light. So if you have this question in your head, well, are all of these colors contained in white light? Yes, they are.
In fact, when the light goes through that piece of glass, the prism, it's just like how it's going through something like water droplet. It gets bent different amounts for the different wavelengths of light inside of white. So we know that white light is a combination of all the colors of a rainbow. And so all those different colors with the different wavelengths move through something like a water droplet or a piece of glass differently. And in fact, I have a demonstration of my own here where scientists have taken the complexities of a water droplet or a prism and made it just a simple piece of plastic. And there's something very special about these glasses I have here. Let me actually zoom in for us. Is that if we look at this special piece of plastic and I were to say show you my flashlight, a source of light, so I'll turn on my cell phone, you can see that it's shining this light. And if I were to put the glasses on you, the viewer, there we go. You can see now all the rainbows coming out of this white light from my cell phone. The whole spectrum, as we call it, the whole rainbow, from red to blue. And we go from red to orange, yellow, green, blue, and violet. The violet's very hard to see, it's not very prominent. But this shows us all the rainbows inside of the white light of my cell phone.
So, Nick, if you had one of those glasses and you held it up to any light source, would you get a rainbow?
In fact, you would. So if I had these glasses on and I was walking around at night, I could look at the moon and I could see the sort of spectrum, the rainbow of the light coming off of the moon. And I could look at street lights, I could look at car lights. If they were red lights or yellow lights, they would change the rainbow. So red light would look more red, and a blue light would have more blue lights inside of it. So I would see less of the red and more of the blue. And so you can use prism spectrum glasses like these, or you can, if you were looking at a rainbow, you're using water droplets to do the same thing. You can look at all the colors of light inside of the beam of light that's going through it.
So that's why we see rainbows oftentimes after it rains. And the light that is being split up when we look at a rainbow comes from the sun. And for that reason, rainbows will always be opposite the sun from where we're standing on Earth. And Nick can show us what that looks like on the screen.
Yeah, so in this case, you might remember from the previous pictures, which I'll bring back those very quickly, that the light goes through the water droplet and bounces off the back of the water droplet and comes back toward us, but at an angle, a 42-degree angle or a 40-degree angle in the case of blue light. And so when the sunlight goes all the way through the water droplets of the clouds and then reflects back to us, it's not reflecting perfectly back at us, it's reflecting at this angle. But you notice how it had to bounce back at us, meaning that the rainbow is opposite the sun. It's acting kind of like a mirror. So we'll never see a rainbow that is in the same direction as the sun. We would see other things like there's certain things called halos and whatnot around the sun, but we'd never see a rainbow in the same direction as the sun. And we can show that too. So let's actually go to our sky. If we were to go to our planetarium sky right now at noon, beautiful, we can see a brilliant blue sky, the sun high up in the sky, and let's imagine this is just after it rains, just after it rained, and we imagine that the clouds are kind of imaginary here. We can't see any rainbow because the sun's too high in the sky, and we need to let the sun set a little bit before we can see a rainbow start to appear. Remember, a rainbow always has to be opposite the sun and then off by about 41 degrees. There we go.
There it is, coming up from the horizon.
So we're fast forwarding through time very quickly here to get the sun near sunset. So we've moved from noon all the way to sunset in just a matter of seconds. And now you can see the rainbow opposite the sun and off by about 42 degrees, 41 degrees. Going from red to violet and all the way across the sky.
So is this what sunlight would look like through a prism?
Indeed it is, a little bit. Depends on whether you're on the ground, if you're in space. Because the light has to go through our atmosphere, has to go through dust in our atmosphere, has to go through ozone and smog and lots of different things. And has to go through the water droplets itself.
So what
Pure
would
sunlight looks a little bit different.
we're in space?
Yeah, what would pure sunlight look like from space? Well, we have this picture of what that would look like if we were to send light through a prism in outer space.
That's an awesome image, Nick. So I want to talk about this for a little bit. This is almost a complete rainbow. And like he said, it's what we would see if we diffracted or split up all of the sun's light from outer space above the atmosphere, which can distort the light a bit. But we see some features in this rainbow. There are some black lines, and that's not a problem with our instruments or our detection. Those black lines are called absorption lines, and they're missing colors. And why are they missing? It's because they have been absorbed somewhere between the light leaving the sun and the light hitting our telescopes. And this would be in the sun's atmosphere. The sun has its own atmosphere and absorbs some of these specific wavelengths. Remember, color is wavelength.
Some of these black lines you're saying they're missing colors because there are things, certain elements around the sun. Just like how we have an atmosphere of air on Earth, the sun has its own sort of atmosphere around it that absorbs some of these colors.
Yeah, you said something really important, elements. So let's talk a little bit more about how much we can learn from these absorption lines. Each element in the periodic table has its own set of lines. It's kind of like a barcode. It's very unique. And so nitrogen, for example, has a certain set of lines, and oxygen does as well. And so if we can find where they are, which wavelengths they're at, we can figure out exactly which elements are in the sun's atmosphere.
Very interesting. So we could do that for the sun's atmosphere, and we could tell what are the different things in the atmosphere just by looking at where the black lines are. So if we saw some that were missing from certain places, like yellow or green, we would know that that is equal to as one element as compared to a different one.
Exactly. So Nick is showing us this pretty helpful picture to visualize what happens when light leaves a star or our sun and passes through things in space and reaches us. So when we're looking at the lines that you saw in the solar spectrum, the cloud of gas that it was passing through was the sun's atmosphere. And the prism is our light detection, our diffraction our diffraction tool that we have in space, much like Nick's fancy pair of glasses right there. But if the atmosphere wasn't in the way, we would just see a continuous spectrum, like the one on the bottom left right there.
Yeah, so if we just looked at pure light from the sun without any atmosphere, it just went straight through a prism like this, we would see a complete and total rainbow. The sun makes all the colors of the rainbow, but it's that atmosphere around it that makes it so it absorbs some of those colors.
And there's actually another cool thing we can learn from these absorption lines. Nick, can you put up another visual that will help us understand what light does when it's in motion?
Absolutely.
So here we have 3 spectra. The plural of spectrum is spectra. And they look very similar to each other. If you look at the one on top and you see the separation between each line, and then you look at the one on bottom, they are kind of the same, except they're all shifted towards the right. And the second one, they're all shifted towards the right. And then the one on the bottom, they are all shifted towards the left. So if these lines have the same separation and they're telling us these certain elements are in the atmosphere that the light is passing through, then it would only make sense that the shifted spectrum is the same thing. So why is it shifted? It's actually because light is either moving toward us or receding away from us. Let's go back to that visual of the wavelengths that we were looking at the beginning of the show.
Hold on, that's the wrong one.
Oh, we're getting there. Right, so if we look at green light and imagine the light source is moving towards you and the wavelengths are compressing, they're getting shorter. So green light will shrink and then the wavelengths will actually look more similar to blue light. And if you're standing here and the light is moving away from you, these wavelengths will stretch out and green light could look more like red light. And this is called the Doppler effect. And we can see it right in that picture of the shifting spectra that we saw. If the light was moving fast enough, green light could look blue if it's coming towards you, and if it was moving fast enough away from you, it would look red. And this is exactly what we've observed looking up into the night sky, aiming our telescopes at distant stars and galaxies.
So it looks like if we were to keep shifting these lines, like if there was something, say, moving away from us a whole lot, say very, very fast, then this redshift would push these black absorption lines so far that they don't even appear on the colors of light I can see anymore. So like what is over here in this direction? Or if I were to make it move faster toward me, blue shift it, what's off over in this direction of the graph?
Yeah, that's a great question. What else is there other than just the colors that we can see? We know that some insects see different colors, some animals see different colors. So is there more to the rainbow than just what we can see with our eyes? And the answer is yes. So let's look at something called the electromagnetic spectrum. This is all forms of light beyond just the visible form, which is what we see. And it ranges from gamma rays, X rays, UV, infrared, microwaves, and radio waves. So you'll see that visible light, which is zoomed in on the bottom of the image, is just a tiny sliver of this huge spectrum of all different kinds of light and a wide range of wavelengths.
So what you're saying is that this is all the light I can see. I can see all these colors from violet to red, and all of them together make up white, of course. Um, and different color combinations can even make like pink and brown and gray, stuff like that. But if I were to somehow look off this side, like something is more purple and more violet than violet, I would see ultraviolet. And the other side, if I looked redder than red, I would get infrared.
Exactly. And if you're familiar at all with infrared, you might know that it is light manifested in the form of heat.
So we can see mostly colors from the sun as just our violet to red, but we actually know that the sun puts out all these different types of light, right? There's not just the visible part of the sunlight. It puts out all these different types of light. But why is it then that I can't really see these? Why is it then that we don't have, say, telescopes to see all of these things for us?
Our eyes can't see them. They don't have the capability to detect all of these different kinds of light, but
Ah,
we can detect these wavelengths with our instruments. And if we want to view them, we can shift them, just kind of like the Doppler shift we were just talking about. We can shift our measurements into the visible part. So if you ever see pictures that say, oh, this is a map of radio waves or a map of UV radiation, and you're wondering, how do we know what that looks like if we can't see it? Well, we take the measurements and then we shift it into the visible part of the spectrum so that we can understand it.
interesting, because that's how we can actually only see those colors. Now, there's some things like it's like goldfish. I've heard they can see some infrared or ultraviolet light, and especially as amazing creatures like mantis shrimp, they can see very many different types of light than we can. As for there are creatures that can see less light than we can, like for instance dogs, they can only see about 1/100th the number of colors that humans can see, and that means that if they were to try to do their own version of astronomy, they would have to use an even more limited color set than we have here. I
That's
can
right.
imagine what the world would look like with fewer colors, like looking through it, what a dog has without having to use, say, like some special instruments, or there's some special software out there that can imagine what it'd look like if you could see fewer colors, and even some that try to help you imagine seeing more colors. But those become kind of wacky.
Yeah, it's interesting to imagine what the world would look like if we could see twice or five times as many colors as we can right now.
Mhm. Now, there's one last bit here that I think is really interesting. I've heard that since all the light from the sun, besides some of those wavelengths that get absorbed, they could make it through our atmosphere, right? So we've got our whole rainbow here, and it can make it all the way to the ground, all the way through the atmosphere. But there's this sort of graph going along here showing things that don't get through. So we can see some of, in this case, the spectrum is actually flipped from the previous graph that we showed you. Now ultraviolet is on the right-hand side. This is what gives you sunburns, X-rays and gamma rays, very dangerous for you. All of these are being absorbed by the atmosphere. So it looks like,
It protects us from those wavelengths?
yeah, the atmosphere protects us from these wavelengths. It's interesting to think that what little bit of ultraviolet light does get through the atmosphere is what gives you the sunburn. What might give you, a very bad burn or cancer. You just have to be very careful of getting too much sunlight. And so the ultraviolet light is mostly absorbed by the atmosphere, but not entirely. As where the less dangerous forms of light, like infrared, microwaves, and radio waves, those a lot of those get through our atmosphere just fine, and we don't really mind so much.
So, what Nick is showing us right now is a huge reason why we send telescopes into space above the atmosphere. We need to get them past this barrier, which absorbs so many wavelengths of light, to detect that light and give us information about our universe.
I think we should take questions.
Yeah, okay, so we are going to start with the question portion, and I think we only have a few today, which is great. um, First, we have from Denise asking, how does the hole in the ozone affect light?
That's a great question. As I said here, that the atmosphere absorbs almost all wavelengths of light except for like visible and some radio waves. You can see that on the graph. The higher this peak, the more it gets absorbed. The ozone layer just so happens to be really, really great at absorbing ultraviolet light from the sun. So that means that the ozone layer is what it is it's 3 oxygen atoms combined high up in our atmosphere. It absorbs a lot of the dangerous light coming from the sun. And back in the 1970s and 80s, when we were so worried about polluting our Earth and with chlorofluorocarbons, CFCs, they would destroy the ozone layer. And if we destroyed the ozone layer, a lot more of that dangerous, harmful ultraviolet light would get through, and it would be irradiating our skin and hurting animals and plants across the planet. It'd be very, very bad. So the fact that we helped to stop that happening, the ozone hole, as we called it, where a lot of it was getting depleted, especially around the North and South poles, has almost entirely healed. So our ozone in the Earth's atmosphere is almost entirely back to the way it was before we started polluting it. And that means that we're very safe from our sun, as we should be.
Yeah, it's awesome to be safe from our sun. All
I don't
right,
want those penguins to get sunburned.
me neither. They don't deserve that. Our next question is from Mr. McFarland, and it's about the Doppler effect. So, Mr. McFarland asks, does the redshift of a sunset or sunrise get created by changing distances of the light source as related to the viewer, while the blue sky is also a shift representing light as we are closer?
His question is asking, like, is the red from sunsets and the blue from the sky caused by the Doppler shift?
Yeah, that's exactly what he's asking.
I see.
So, let's start by breaking this down a bit and answering the question, why is the sky blue? So if we remember that wavelengths are scattered differently, blue is actually scatters easiest. So if we have a light source up here, and I'm going to use this little sphere as the Earth, this top part would be the daytime sky, and blue would scatter across the daytime. And then there are still wavelengths left over from the white light, and these come in on the sides where it's sunrise and sunset. This is what creates the beautiful phenomenon that is sunrise and sunset having these oranges and yellows and reds, while the daytime sky has the easy to scatter light, the blue light. Doppler shift is motion relative to the light source. So if this hand is the light source and we are the Earth moving around the sun, we are not moving toward or away from the sun. So wavelengths aren't compressing or expanding. It has nothing to do with the color of our sky.
We'd also have to be moving considerably fast to see a very large change. But like Emily said, the majority of the reason the sky is blue is just because blue light scatters much more easily through our atmosphere than any other color of light, mostly throughout the day.
Right. Yes, we would have to be going very fast to see the effects of the Doppler shift. If you're speeding in your car, for example, like 90 miles an hour, you're still going to see whether the light is green or red. It's not going to change. Doppler shift is noticed on much, much larger scales, like stars and galaxies.
Especially things that are expanding away from us at very close to the speed of light, things very far away. And to answer the last part of the question about sunsets, is the red from the sunsets caused by that? This is actually harkens back to when the light goes through water droplets, it bends differently based off the wavelength. That the red and the blue bend differently based off of them going through the water droplet. The same thing happens with our atmosphere. That the red and blue light scatter differently when they go through the air in our atmosphere. And so we see that mostly the blue light scatters throughout most of the daytime, but once the sun gets really low on the horizon, the red light is what scatters mostly. And so the yellows, oranges, and reds scatter much more, and then they can hit these clouds and reflect back down to Earth. And so every time you're seeing a sunset, there's red light coming from the sun going through the atmosphere and even scattering out into outer space. So there's always some red light coming from the sun wherever there's a sunset. That's because of our atmosphere.
Yeah, our atmosphere plays a huge role in how we see light here on Earth. And Jessica asks now, can rainbows be seen on other planets? And the answer is yes. This phenomenon can occur anywhere where light is being refracted. And so if you're on another planet and there's an atmosphere, and maybe there's some kind of rain, maybe it's not even water rain, it will refract the light and split up wavelengths into a kind of rainbow.
It's interesting to think that no matter what light is going through, it's always going to shift differently, that the wavelengths are always going to spread out. Whether it were to go through, say, my very special glasses here, or if they were to go through a prism, the atmosphere, water droplets, even my own eye, every single thing that light goes through, it will end up splitting apart into different colors. It just depends on how much it does that. And so you can see that when you're, say, looking underwater and looking through water droplets, glass, lots of different things.
So I think we're about out of time. Thank you everyone for tuning in. Thanks for your questions. I want to finish this show by just reminding everyone to practice empathy and be kind to one another, and remember to listen to the world around us so that we can make it a better place.
Thank you, everyone.